groups of order 6. Okay. So I decided against it, mostly because I think it is better to develop enough stuff to prove Silo theorem and then revisit this problem. In the meantime, I figured out a simplistic calculation, relatively simple calculation, but sort of when one has to do, not rely on theorems, which will tell you what the groups of order. There are two non-isomorphic groups of order 6, so that I will add as an exercise. Actually, I've already posted the exercise. There is a typo, but I will fix it when I update more problems. Okay. So we'll revisit this problem about let's say groups of order 6, order 8, 9, 10, okay, 12, etc. After we prove zero theorems. Okay. At least some easy versions of zero theorems. Okay. So let us start think towards that. Okay. So I'm going to introduce what is called group actions. Okay. This itself is, zero theorem or proof of parts of zero theorem is just one application of this. This itself is an important concept. Okay. You will see in many contexts, groups acting on things, groups acting on sets, groups acting on vector spaces, okay, etc., etc. Okay, so this itself is an important notion in this. Okay, so let G be a group. Yeah, this itself is an important notion, and proving zero theorems is just one, or proving some part of zero theorems is just one application. But we will prove. So we will do this in some generality, try to understand some generality, but then we will tailor it towards towards the proof of zero theorems. And also, there's no lecture on Thursday, it being a CMA holiday. Also, the first Tuesday of May is also a holiday. So out of these two, I would like to make up at least one lecture. But I'd like to wait till the first week of May just to see if I really need to make up. And also, it'll give me more time to sort of conclude the course if I make it up at the end. So we can discuss a suitable time later. Let G be a group. And let X be a set. We say that G acts on X if for every G in G, there are functions phi G. Okay, so this depends on G from X to itself, satisfying the following. Okay. Phi, the function corresponding to the identity element 1. Okay, so maybe hereafter I'll stop writing E. I'll just write, if I'm writing the group with multiplication as the operation, I'll write 1. If I'm writing a group with addition as the operation, I'll write 0. Okay, so this is a change in notation, and this is also more consistent with how most people use. We use E, etc. at the beginning, just so that the thing is clear in our head. But once we understand it, we just call it 1 if it's multiplication, we call it 0 if it's addition. The group operation is thought of as addition. So the function corresponding to 1, okay, is the identity map X to X. In other words, every little x goes to itself. Okay. And B, for all G1 and G2 inside G. Okay. What is the function corresponding to G2, G1? this is the composition of function corresponding to G2 G1. Okay. So this is first apply the function corresponding to G1, and then you apply the function corresponding to G2, and the composite is the function corresponding to G2 G1. So remember the order in which it is. Okay. So this is okay. So this is what we mean by saying a group G acts on a set X. Okay. So for every G in G, there is a function satisfying these two. I mean, for every G in G, there is a function phi G satisfying the entire family together satisfies these conditions. So let us look at an example. In fact, the most canonical example. We'll see more examples after we make some remarks about this. Sn acts on 1 through the set containing 1, 2 through n, okay, where a permutation corresponds to the function which does that permutation, okay, naturally, in a natural way. A permutation, I mean, this is sort of tautological, but it is important to understand this in this language. Permutation, sigma in Sn corresponds to the function in which takes I to sigma of I. So, I mean, a permutation itself is a bijective function. Okay. This is, I mean, the example is tautological. This is, I mean, such functions is exactly what we call permutations. Okay. But it is important to understand that to sort of think of this as a group acting on a set. Okay. So this is one. So this is sort of a basic example, essentially tautological. So I want to make so this is example one. I want to make a remark about what this actually says. So this one says that if you take G2 to be G1 inverse, then phi of 1 is phi of G1 inverse composed with G1. Remark. Okay. So with notation as in definition. Okay. Note that phi of G composed with phi of G inverse. This is phi of G inverse. That is the way the composition works. But G inverse is 1. This is the identity function on X.
Sir,
yeah.
In example 1, is phi of G equal to G?
Correct. Yeah. I mean, yeah. So this I am thinking about as the function phi of sigma. But it is sigma. I mean, sigma permutations are functions, right?
Okay, sir.
Yeah. That's why I said it is a tautological example, but we would still like to think about this as a group acting on a set, just to become familiar with this idea. Is it clear now?
Yes, sir.
Yeah. This function that I wrote here is what we denoted as phi of sigma, okay? But it is the function sigma. And okay, so phi of G inverse composed with phi of G is phi of G inverse G is phi of 1 is again identity of this. Okay. Therefore, for all G in G, phi G is bijective. Okay. So although I did not say that these functions are bijective in the definition, it is immediate from the definition that these functions are bijective. So in other words, So now, let me not write it. I will write it properly in an exercise so that you can think about it and work through it. In other words, every G in G corresponds to a bijection of X to itself in some compatible way. In some compatible way. Phi of 1 is 1 and phi of a product is the composition of the products. Okay? It is actually a bijection. But we saw earlier that bijections are exactly permutations. Bijection is another word for saying permutation, right? So there is a relation between group actions and permutations. So which I will outline in an exercise that is not really crucial for understanding the concept. So I do not want to elaborate it during the lecture. Okay? We can revisit this at a later point. But right now, just think about this. Each group element gives a function from the set to itself, satisfying certain compatibility relations. And it follows immediately from the definition that these functions must be bijective. Okay. So more examples. In fact, many natural things that you have studied so far are examples of group actions, though not stated in that. Let G be a group and H a subgroup of G. Okay. Then so H is a group and G is a set. Then then H acts on G. Okay. We'll say by translation. Okay. That is just a loose word to denote the following. A group element. So phi of H is a function from G to itself. Okay. So that's what we want. For H inside H. Okay. Phi of H from G to G is the function which sends G to G times H. Okay. So remember the given group is the set. The subgroup is the group which acts on the set, the larger group. Okay. And so this action is often called translation. If you think about it in terms of R, it is just like adding a constant number and moving it left and right. Therefore, for that reason, it is thought of as a translation. Forget about the terminology. Just think about this function. Okay. Given a little h in H, we have a function from G to G, which sends. Sorry. Let me write HG. I'm sorry. There's a slight issue writing the other way around. Okay, HG. Okay, so let us check the thing. Okay. Phi of 1. 1 belongs to H. Okay, this is the function. Is G. This is 1 times G for all G inside G. So phi of 1 is the identity function on G. So this is a notation that I will use to denote identity function. So I already used it here, I think. Yeah. Okay. So ID sub X from X to X is the identity function. Which sends little x to itself. For any set, we will write ID sub that set to denote the identity function. Okay. And if we take, let H1, H2 be inside H, okay, then phi of H1, let's call it H2, H1. It doesn't matter which way we write, just two of them, of G is by definition H2, H1 of G. Because now we are multiplying this subscript, which is an element of H, to G. That's what the operation is. Okay. Multiply the subscript, which is an element of H, to this input, which is from G. Okay. This we can rewrite it as H2, H1G. So this is associativity in G. This group operation is associative. and this is phi of H2 of phi of H1 of G, okay, for every G in G. So phi of H2, H1 is the composite. And this checks the two conditions. We needed to show that phi of 1 is the identity map, and phi of a product is the composite of phi's in the same order. Okay, phi of G2, G1 is phi of G2 composed with phi of G1. So we check that for this thing. That's the case. Sorry, initially I wrote G goes to G times H, but there's an issue. I mean, it can be fixed, but it's easier if you just do it this way. Any questions on this example? Okay. Yeah. So then, okay, so let's look at the next example. Again, these are all very natural things that we have seen earlier. It is just that we have not thought about in this language. Okay. GLNR acts on Rn. Okay. What is the action? Phi of a matrix A for A inside GLNR of from Rn to Rn is the function. I mean, it's the linear transformation given by V goes to A times. So then phi of the identity matrix is the identity map on Rn. Phi of BA of a vector V is BA. So remember, it is BA that has to be the product BA that has to be applied to V. BA times V. That's how the function is. Whatever matrix whose phi we are considering, multiply that matrix with V. This is B of AV, and this is phi B of phi A of V. Okay, this is true for every V in Rn. So phi of BA is phi B composed with phi A. So again, so notice that in these examples, these are bijections. We are taking invertible matrices and we are multiplying vectors in Rn, and that is an invertible operation. Right? I mean, you can multiply by the inverse, and it is a bijective map. Okay? The map V goes to AV is a bijective function when A is invertible, and in fact, precisely when A is invertible. You can invert it back using the inverse of A. Similarly, here we can use it. You can use the H inverse to get back to G. G goes to HG, and using H inverse, we can go back from HG to back to G. So that is, so these are bijective functions. And similarly, SLNR acts on R. That's again the same calculation. Same calculation. I mean, just as an aside, if G acts on a set X, and H is a subgroup of G, okay, then the action of G on X restricts to an action of H. And just general remark, think about it. This is, don't consider phi G for every G in G, just consider phi H for only H in H. That also satisfies the same condition because there it is universally quantified. So elements of H also should satisfy the same. And one is inside H. So this is not a, so the earlier statement, SLN acts to Rn using the same calculation is just an instance of this observation. Okay, so now we want to look at a slightly different example. But again, S3 acts on R2 as follows. So R2 we think of as the x-axis and y-axis. I mean the perpendicular axis in the usual way. Okay. 1, 2. I mean the permutation 1, 2, cycle 1, 2. This is left. Reflection about the y-axis. And the cycle 1, 2, 3 is rotation by counterclockwise rotation. I mean rotation by 120 degrees. And whenever we say degrees, it is always, I mean, whenever we say rotation by some angle, it is always counterclockwise. So 120 means 120 counterclockwise. Or we can say minus 120 counterclockwise also, but that will just mean clockwise. Okay. And we can actually write this using a picture.
Sir, are you defining these?
Yeah. I mean, okay. I'm just saying. Maybe I should not. Phi. Thank you. Sorry. I should have been consistent with my notation. Phi of the cycle 1, 2 is rotation by this. And phi of the cycle 1, 2, 3 is this. Is it clear now?
Yes, sir.
Yeah, I'm defining the action. So I should, yeah, this is the correct way to define it. It is just, some shortcut which is not correct. Yeah. So this is the X and Y axis. And okay, I will label, so I'll draw an equilateral triangle here. So we will come back to this question, symmetries of regular polygons. But okay, so the group of symmetries of regular polygons. So you can think of this as an equilateral triangle. Okay, and I want to label this as 3, this as 1, and this as 2. So that, I mean, the labeling of the vertices is chosen so that it's easy to relate them to this phi of 1, these functions phi and phi 1. Okay. So you can check that this is a okay. So first of all, you need to check that the cycle 1, 2 and cycle 1, 2, 3 will generate S3, which I don't know if I have assigned as an exercise. If you have not, please do it. Okay, check that. The subgroup of S3 generated by 1, 2 and 1, 2, 3 is S3 itself. Okay. So that it's enough to specify what these are. Everything else can be written as a product of these things in some order. It is the smallest subgroup containing. Okay. And check that this is a group action. Okay. I mean, that is because, see, it is a group action because we are, okay, so maybe I should clarify. What are we doing? Okay. We are getting a map from S3 to GLN. Rotation by 120 degrees can be thought of, GL2 can be thought of as an element of GL2. Okay. rotation, but reflection about the axis can also be thought of as an element in GL2, right? It is the one which fixes. So more precise. Maybe let me just add that. I think it is okay. More precisely. Okay. So we have defined a group, an injective group homomorphism. From S3 to GLN, sorry, GL2 of R, okay, in which the element 1, 2 goes to, so this is reflection about the y-axis. So this is the matrix, okay, in which X is multiplied by this, and 1, 2, 3 goes to whatever, cosine 120 degrees, sine 120 degrees, correct? Sine 120, yeah, and then minus sine 120 degrees and cosine 120 degrees. This is when this matrix represents rotation in the plane, right? So this is rotation by 120 degrees, and this is reflection about the y-axis. Okay. So what we have defined, okay, so if you check this, so we've already checked abstractly that GL2R acts on R2. Now we are just saying S3 is a subgroup of GL2R using these maps. Okay. So this makes S3 as a subgroup of GL2R, and as we observed earlier, if a group acts on a set, then subgroups also act on the set, using the same operation. So this is what you check. Any questions? Yeah. So now we come to another important action, probably new, but this is what we will need to use in proving parts of zero theorem, which is let G be a group.
So can you go back to the triangle which you drew?
Yeah.
So I think this triangle should be should have its circumcenter overlapping with the origin, right? Then only the rotation.
Sorry, correct. You're right. My x-axis is in the wrong position. Yeah. It should have its midpoint, which is maybe somewhere here. Yeah. Thank you. Yes. Because you want rotation to preserve the shape of the triangle. This is x-axis. Yeah, this is the center where all the three perpendiculars meet, or all the three medians meet, or whatever. It's an equilateral line. Yeah, thanks. Okay. Yeah, so let G be a group, okay, and X the set of subgroups of G. So we're considering all subgroups of G. Then G acts on X by conjugation. Okay. What does that mean? Okay, so we need to get a map. So okay, from X to X. Okay, so let G be in G. That is for G in G. Okay, phi G, which is a function from the set of subgroups of G to itself, okay, is the function. Which sends a subgroup H to its G conjugate. So phi G is this function. It takes a subgroup, and this is also a subgroup. I think this was one of the exercises, or maybe we discussed in class. So maybe I should just remark here that this is a subgroup. I mean, conjugates of subgroups are subgroups. So this is this function. H goes to G, H G inverse. Phi G is this function. Okay, it is a function which acts on the set of subgroups of G. And so phi of 1 is phi of 1 applied to a subgroup H is just 1 H1 inverse, that is just H for every H in X. And phi of G2 G1 of H is G2 G1. So it is this product G2 G1 times H times G2 inverse, G1 inverse G2 inverse, that's the inverse of G2 G1. But this by associativity is just G2 of G1 H, G1 inverse, G2 inverse. And that is just phi of G2 applied to phi of G1 of H. Just the thing inside these brackets is phi of G1H. And then there's a G2 times this times G1, G2 inverse. That is just phi of G2. So this is an important action that we will need to use when we start proving, when we start studying. I mean, structure of groups. Okay? Not necessarily zero theorem, in various other contexts also. So this is one. Okay. So I'm not going to start proving zero theorem, etc. I think this is already such. You should read through these examples and make sure that you understand this concept of a group action. Any questions on this so far?
Can you go back to the last page?
Could you repeat what you said?
Hello, can you hear me?
Could I scroll up? What? Sorry, I cannot hear properly. Is that what you said?
Yes, sir. Yes, sir. Can you scroll up?
Yeah. How far up? This is okay?
Yeah, this is okay. Yes, sir. I had got it. You can continue.
Yeah. Okay. So there are some notions related to group actions. So the first thing that we need to, think about when we look at this is called the orbit of an element. So definition. Let G be a group acting on a set X. The orbit, so let X be inside X. The orbit of X, okay, for this action, is the set Gx, where G is inside G. Okay, so think of G as just pushing this X, and it is just okay. So as you apply more and more elements of G, you get some larger and larger set. But eventually, okay, so this is the set that wins. Okay, so for example, sort of get a pictorial view of this. Okay, we can think about the action of a cyclic group Z mod MZ on R2, okay, as follows. Okay, phi of some k bar is I mean, so this is some action. Okay? So 1 bar, I mean, 0. So phi of 0 bar is the identity map on R. Phi of 1 bar, because it's a cyclic group, and 1 bar will determine what every other group element does. Okay, so this is given by the element multiplication, I mean rotation by e to the 2 pi I, rotation by 2 pi divided by m. So this is the matrix 2 cosine 2 pi divided by m, sine 2 pi divided by m, minus sine 2 pi divided by m, cosine 2 pi divided by m. Okay. So this is this is 1 bar. Okay. So then phi of some k bar will be rotation by 2 pi k divided by m, and finally when k bar becomes 0 bar, you will just get identity. So in this case, we can actually think of it as an orbit. So for P inside R2, for simplicity, let us say it is not 0. The orbit of P, so this is like an orbit that we think about. Orbit of P is P, then P rotated by 2 pi divided by m, then P rotated by pi divided by m, and so on. Okay. So this is like an orbit. Okay. If you had a P like this, then there will be that. Let us say m is equal to 3. So there will be this point. Then there will be some point here. There will be some point here. Okay. So this is phi of 1 bar P and phi of 2 bar P. So you can think of this as an orbit. So that's where the terminology comes. But in general, it need not have a nice thing like this. It is just abstractly, you can just think of it as the set of points which x is taken to by this action of G is called the orbit of x. Okay?
Sir,
yeah.
So in the above notation, like g of x, does it mean like phi g of x?
I'm sorry. Thank you. Sorry. Yeah. Thank you. Yes. Yeah. Phi g of x. Okay. Yeah. Eventually, I mean, for this course, I will definitely try to keep notation like this so that it is clear in our heads that we are thinking about functions. But eventually, we will drop this. I mean, it may not be when I teach you, but we will all drop this. Just think of it like as gx. Yeah, but now let me write the elaborate notation to sort of make it clear that we are discussing some functions from x to itself. Okay, so this is what we mean by orbit. Okay, so I so proposition. We can define an equivalence relation on X like this, and the equivalence classes are exactly the orbits. So let me say, let G be a group acting on a set X. Let this be a relation on X given by X1 is related to X2 if there exists a G inside G such that X2 is g times x, phi g times x, phi g of x. Okay. So we are saying that there is a function phi g corresponding to a group element which takes x1 to x2. If this is the case, then we say x1 is related to x2. Okay. Then the equivalence classes of sorry, I should not say. Let me state everything. One, then one. This is an equivalence relation. Okay. Two. The equivalence classes of this are precisely the orbits of G in X. Okay, so I mean, we defined the orbit of an element, but when we consider all the possible orbits, we just call it the orbits of G in X. Okay. So I hope. Okay, so this is G in X. So proof. One. So we need to check three things for checking that it is an equivalence class, equivalence relation. We need to check reflexivity. Okay. For all x inside x, x is identity times phi of 1 times x, because phi of 1 is, okay, so x is related to x. So this is A, B, symmetry. For all x, so let us just do, so let x1 and x2 be related. Okay. Then there exists G inside G such that x2 is phi g of x1. Okay. This implies that, so let us compute, okay, phi g inverse of x2 is phi g inverse of phi g of x1, which, because it is a group action, it is phi of g inverse g of x1, which is phi 1 of x1, or phi 1 of x1, which is x1. Okay. So x1 is phi something of x1, x2. So x2 is related to x1. That is the symmetry condition. And C, transitivity. So let x1 be related to x2 and x2 be related to x. So therefore, there exists G1 such that phi G1 of x1 equals x2, and there exists G2 such that phi G2 of x2 equals x3. Okay, this is what the two conditions mean. Therefore, phi G2 G1 of x1 is phi G2 of phi G1 of x1. That's what we mean by phi corresponding to a product element in the group. Okay, so this is phi G2, this is x3. So therefore, x1 is related to x3. So therefore, this is an equivalence relation. So this proves that. So now let us look at the equivalence classes. Yeah. Okay.
Hello, sir.
Yeah. Yeah.
Sir, what do you exactly mean by orbits of G in X?
Okay, okay. So maybe I should clarify. So for X inside X, the orbit of X for the action of G is the set phi G of X as G is inside G. Now one can consider this. Fix an X, take the orbit. Take some other X, take its orbit, and so on. So consider every subset of X, which is an orbit of some element of that set. Okay. So a subset x0 of X is called an orbit of G in X. Of course, all of this is understood for a given action of G. G is given, X is given, and what is the map phi G for each G is also given. Okay. Orbit of G in X is called an action orbit of if there exists X inside X0 such that X0 is the set. Okay. This is what we mean by orbits of it's called so the orbits of G in X are exactly those subsets that satisfy this property. Does that clarify?
Yes, sir.
Okay, okay, maybe before we prove this thing, before we prove, let us clarify this. Okay, so let's go back to this example, this picture where we. Okay. So. I'm just considering this example itself. Okay, this picture. Okay. So, if you consider this point, 1 0, then 1 0, then this cosine is minus half square root of 3 divided by 2, and minus half and minus square root of 3 divided by 2 is an orbit of 3z in R2. Okay. 1 0 0 0, then get to whatever you want, is not an orbit of z mod 3z in R. Do you see the distinction between these two sets and why one is an orbit and the other one is not an orbit? Hello?
Yes, sir.
Huh? Is it clear? See, the first set is what? 1 0 is a starting point. If you apply phi 1 bar, it will rotate by 120 degrees. So you'll get this point. And if you apply phi 2 bar, it will rotate by 240 degrees and we'll get this point. And phi 3 bar is anyway phi 0 bar, which is identical. That's an orbit. While the second one is not, because there is no group element G, such that phi G will take 1 0 to 0 0. Is it clear? Maybe. There does not exist any G inside 3z such that phi of G of the point 1 0 is 0 0. So this is not the orbit of anything. Yeah, okay. Okay, it may depend on what you fill in here, but it wouldn't matter. Okay, that is an exercise. It doesn't matter what you fill in here. There is no way a group element can take a non-zero vector to 0, 0. So this is not an orbit. Is it clear? What subsets we call an orbit and what subsets we don't call an orbit?
So these are regarded as orbits of Z mod 3Z, right? I mean, not of the
Yeah, yeah.
element 1, 0 or nothing
No,
like that.
Correct. It is the orbit of one. I mean, the first one is the orbit of 1, 0. So therefore, we say it is an orbit of Z mod 3Z in R3. Meaning it is an orbit of some element of R3 for this action of Z mod 3Z.
Okay. So
I mean, see, we may want to consider some subset of R2, not R3, some subset of R2 in which some element can give all the other elements by this group action without specifying what that element is. Yes, when we say it is an orbit of Z mod 3Z in R2, we mean there exists an element in R2 whose orbit this is, without specifying what that element is. I mean, is that clear? Yes, it is an orbit of some element.
yes, sir. Now
But I
it's
don't,
clear.
I mean, for this point, we don't care that what specific element that is. We just say it is an orbit. Okay. Well, the second one is not, because there is no way from a non-zero vector we can get 0, 0, or from a 0, 0 we can get a non-zero vector using this action.
So in the second one, for no G, I mean, there does not exist any G such that phi G acting on any element gives 0, 0, right?
No, any non-zero element will give 0, 0.
Yes, sir.
Or vice versa. Any element acting on 0, 0 will give 1. So as soon as there is 0, 0 and a non-zero vector, we can conclude that it is not an orbit of this action.
Oh, yes, sir. As the phi G is bijective.
Yeah. So that's what we mean by orbits of G. Yes, we are considering orbits of elements of X, but I mean, we may not always want to specify what that element is. Just have to say it is the orbit of some element. So then we just say it's an orbit of X, orbit of G in X. Now is it clear?
Yes, sir.
Okay. No, it is important to understand definitions before we set out to prove statements. Yeah. So now we want to claim that every equivalence class is an orbit and every orbit is an equivalence class. Again, once we start writing out the proof, you will see that this is just tautological statements. I mean, the equivalences are sort of clear, but again, let us just, it's a good exercise to write the. Okay. So let x0 inside X be an orbit of G in X. Okay. That is, there exists some X in X0 such that X0 is phi G of X, where G is inside G. Okay, so now we want to show that this is an equivalence class. So we want to show that things inside this are equal, are related to each other. And moreover, if something is related to any of these elements, then it must be inside X0 itself. Okay. So we want to show that X0 is an equivalence class. So let X1 be inside X, a point. Then, by definition, X is related to X2, X1. right? Because x1 is of the form phi g of x for some g in G, therefore x is related to x. So elements, okay? Sorry, I need to consider two. Sorry, correct. I need to consider two elements. Let me write. X1 and x2 be inside x0, then okay, there exists G1 and G2 inside G such that xi is phi gi of x for I equals 1 and 2. Therefore, x is related to x1 and x is related to x0. By symmetry and transitivity, x is related to x2. Okay. By symmetry, this is an equivalence relation that we have already verified. By symmetry and transitivity, x1 is related to x2. Okay. So every pair of elements in this set x0 are related to each other. Okay. That's so. Okay. So this means that x0 is a subset of some equivalence class. Now let y in x be such that x is related to x is related to y. Remember, x is the one whose orbit this x0 is. Okay. So what we have checked is elements in the orbit are related to each other. That's what we have just checked. We would now like to check that elements outside the orbit are not related to each other. Or in other words, anything that is
Sir,
related.
why do we need to show that x1 is related to x2 over here? I mean,
because we want to show
if
that
we
this
have x and any element in this set is related to x, then that's enough, right?
That is enough. But I mean, by an equivalence class, we mean a subset in which every pair is related to each other. I agree.
Okay.
If you just check
Okay.
for a fixed element, then by symmetry and transitivity, every pair will be related to each other.
Yes, sir.
And I have not used anything more than that.
Okay.
Yeah. I mean, yes, you can say there is an equivalence class if there is an element to which everything is related, or you can say in every pair the two elements are related to each other. They're equivalent by symmetry and transitivity. I have not used anything more than that. So suppose that there exists related to y. So the equivalence relation is that, I mean, it's exactly the statement, right? There exists a g such that y is phi g of x. Therefore, there exists g and g such that y is phi g of x, which actually implies that y is in the orbit. Therefore, the equivalence class containing x is x0. That's what we just showed. In any equivalence relation, there is a unique equivalence. I mean, given an element, there is a unique equivalence class containing that element. Okay, the equivalence class of x is x. So we have shown that an orbit is an equivalence class. Equivalence class. Okay. Converse is again a similar, essentially tautological calculation. Conversely, okay, so now we need to take an equivalence class and show that it is an orbit. Let y inside x be an equivalence class. Okay. So let x be inside y. So this is an equivalence relation. Okay. So for every little y in y, so the equivalence relation was this. Okay. Two things are related if there is a g satisfying this. So this I want to fix then. For every y inside y, there exists g inside g such that y is phi g of x. Right? That is because, I mean, correct? I mean, x is related to y. So therefore, this is what it means. This implies now that y is in the orbit of x. And again, we just have to check for one element because the yeah, so maybe we could have probably written this proof in a slightly cleaner fashion, but I didn't include it in the explanation. Maybe it is easier to prove the following statement. For every little x in x, the equivalence class of x is the orbit of x. So let me finish the proof here, but I just add as a remark, as an exercise in cleaning up the proof. See, often when we write a proof, it may not be the cleanest proof that we can think of in cleaning up the proof. Okay. One can rewrite the above arguments show the following. For all x in x, the orbit of x is the equivalence class containing x. Okay. And this proves that all equivalence classes are orbits. I mean, the set of orbits is exactly the set of equivalence classes. Because given any equivalence class, it must be the equivalence class of some x, and then therefore it is the orbit of x. Conversely, given an orbit of x, given an orbit, it must be the orbit of some little x, and therefore it is the equivalence class. So this will prove that. Okay, already proposition. Yeah. So let us go back to those examples. So back in the above examples. Wait, so let's say back to the examples. One, Sn acting on 1 through n. So there, for every element j and for every k, there is a permutation which sends j to k. Okay. For all 1 less than or equal to j less than or equal to n, and for all 1 less than or equal to k less than or equal to n, there exists a sigma such that phi sigma of j is k. That is just saying, for example, take the transposition which transposes j and k and fixes everything else. That would satisfy this condition. So, for example, take the cycle jk. Okay, this has this property. So this is okay. So therefore, 1 through n is one single orbit. Is a single orbit. So this is one example. So we'll just go by slowly one example at a time. G group, H subgroup, okay, acting on G. By sending G to G, phi H from G to G is G goes to HG. So what are the orbits? Okay. So for G in G, the orbit of G is the set HG, H inside H. Right? This is what is phi H of G. But what is this set? Okay. This is the right coset. Coset of H containing G. Okay. And we have already seen left cosets are equivalence classes for that equivalence relation. Right cosets are equivalence classes for some other thing. So these are okay. Okay. Yeah. So these are the right cosets. And 3, GLN acting on Rn. If V and W are non-zero vectors in Rn, okay, then there exists an A inside GLN, GLN R such that W is A times V. Okay. Therefore, all non-zero vectors form one orbit. The orbit containing 0 is the singleton set 0. Any question on this? Sorry, was there a question when on this thing? Okay. So the remaining 2 examples, which is S3 acting on R2, it is just similar versus some S2. Okay. So the other one, a group acting on the set of cosets. What are the orbits? Okay. So that we'll just do one example. Okay. So this is 5. Let G be a group and X the set of subgroups of G. Okay. Suppose H is a subgroup of G is such that and G acts on X by conjugation. Okay. Suppose H is inside X is such that I'm asking, looking for a specific H with a specific property such that its orbit. Of course, any element belongs to its own orbit, okay, because it's identity. Phi identity times, phi identity applied to that element that little x is that itself, right? So its orbit is itself. It's a singleton set. There's nothing else. Its orbit is a singleton, like this one. Here is an example of an element whose orbit contains just that, nothing else. So what if? Then what can we say about H? So what does this mean? This means that for all G inside G, phi G of H is H. But what is phi G of H? This is GH G inverse. But what does this condition say? Okay. Therefore, orbit of H is a singleton if implies this condition, phi GH G inverse H. H is normal. Okay. This we had proved that a characterization of normal subgroups is this. Okay. Conversely, if H is normal, then GH G inverse is H, okay, for all G inside G. But this is exactly the group action. Then, so okay, orbit of H is a singleton. So actually, this is an equivalence. I mean, the red thing was, I mean, the proof written below is the proof of the red arrow, red direction. Okay, so I'll stop here. This is a lot of new things. So please make sure. So there's no lecture on on Thursday. So please make sure that you read this and understand at least. Okay. If you have questions, you can email me. I can clarify. Okay. So please make sure that you are able to read this and understand. As I said, most of the examples there is nothing new. Okay. I mean, except this conjugation part. It is just sort of written in a new language. So please make sure that you are comfortable with this language before next Tuesday. So I'll stop.
Sir,
Yeah.
regarding the last example, sir, I had
Yeah.
a question. Yeah.
Yeah.
So, if a group does not have any normal subgroups, then
There won't be any singleton orbits.
all orbits will be
We'll have at least two elements.
okay.
Yeah. It has no normal sub. I mean, yeah. Singleton orbit is the characterization of a normal sub.
Okay.
Yeah.
Thank you, sir.
Yeah. So